Hello and welcome to my presentation. My name is Godwin Ekuma and I'm a computer science graduate student at Missouri State University. My presentation is based on an explainable deep learning prediction model for severity of Alzheimer's disease from brain images. And this research work is supervised by Dr. Tayo Obafemi Ajayi. AI and deep neural networks have been successful in creating predictive models for precision medicine. However, most of these AI models do not eventually make their way into clinical practice due to the black box nature of deep neural networks, causing lack of understandability and interpretability of the models. So, this research work is focused on building an explainable deep learning model to predict severity of Alzheimer's disease by analyzing magnetic resonance imaging of the brain. Alzheimer's disease is a neurological disorder that damages the brain cells, causing language, memory, and thinking problems. And this disease is known to account for 60 to 80% of dementia cases in the US. This disease exists in a continuum, with the first stage of the disease called the clinical normal stage or the CN stage, the next stage, the minor cognitive impairment or MCI stage, and then the last stage is the dementia stage due to Alzheimer's disease or AD. Our motivation for engaging in this study is that AI relies on large amount of data in order to produce excellent results. However, in medical imaging, we do find that there are not a lot of available MRI images relating to Alzheimer's disease. Also, there are a large number of different neural networks. Selecting the one that is best suited for analyzing magnetic resonance images for Alzheimer's disease prediction is also still a challenge in research. And also, like I did mention previously, there is lack of interpretability of these deep neural network models, which creates some form of skepticism and hindering their adoption in clinical practice. So our goal in this research is to build is to construct a deep learning framework which will predict Alzheimer's disease severity, and then integrate a local data interpretation method which uses sharply additive exploration values to explain the relationship between a predicted Alzheimer's disease severity and the given input image. We also conduct a comparative analysis of 3 different deep learning networks in order to determine which network is best suited for Alzheimer's disease prediction from MRI analysis. In order to achieve our set objective, we utilized a data set from the Alzheimer's disease neuroimaging initiative database, and then we standardized the data, the size, the shape, and orientation of the data, and also removed non-brain tissues that existed in the images. And then we utilized a technique called transfer learning with 3 different pre-trained deep neural networks, namely the DenseNet 121 network, the DenseNet 169 network, and the Inception ResNet V2 network. Because these networks were pre-trained on a different classification task, we fine-tuned these models or these networks to suit our own classification problems. And of course, that added a final layer for classification. After training our model, we passed the model into the trained model and the deep neural network into a deep explainer based on sharply additive explanation values to help explain the relationship that exists between the predicted outputs and a given input image. After training our models, we found that the 3 different networks that we had considered during the course of our study performed comparatively in terms of their training. However, when we tested our models on samples that were not seen during our training, we found that the Inception ResNet V2 actually outperformed the other 2 models. We also further evaluated our models using other model evaluation metrics, namely sensitivity and specificity. Sensitivity measures the true positive rate of your model prediction, Y specificity measures the true negative rate of your model prediction. And we found that the inception ResNet V2 model actually had a balanced sensitivity and specificity across all the different severity groups. We now further pass these models into the trained model and the input images into Sharp Deep Explainer, which generated visualization, pixel visualization of the different regions of the brain which the deep learning model focused on in making its decision. And when you look at the different predictions, you would find that they are both red pixels and blue pixels. The red pixels indicates positive correlation, and the blue pixels indicates negative correlation. And the degree of intensity of the pixels indicates the intensity of the colors indicates the degree of impact in which that particular pixel had in the decision of the model. When Alzheimer's disease progresses, certain regions of the brain, such as the cortical sulci and the ventricles, begins to widen, and then the corpus callosum begins to thin up. The red pixels that we observed around the ventricles and the cortical sulci indicated that the neural network relied on those regions of the brain in making its decision. And we also found by analyzing the results of our model that the inception ResNet V2 network is best at predicting the various severity groups that exist within our data set. And then, of course, with integrating the Shapley additive explanation values, we are able to increase the confidence of the understandability of our model. Thank you for listening to my presentation.